Hello everyone, and welcome to this talk. My name is Slobodan Vrkačević and I'm one of the software developers here at FrogLogic. In this talk, we'll take a look at code coverage on MCUs or microcontroller units. The talk will be a little bit more for the beginners or colleagues who are starting with this topic. Because of that, I will first talk a little bit about some basic concepts, then we'll see how to set up and use Coco on MCUs. There will be a little live demo and I'll talk about some common problems and challenges. So let's talk first about some basic concepts like what are MCUs and what is code coverage. I noticed that some colleagues confuse a little bit MCUs with things like Raspberry Pi or single board computers, and the main difference between microcontrollers and single board computers like Raspberry Pi would be that everything is actually included in the chip of the microcontroller. So everything inside of bigger computers like RAM, memory for program like flash, and some other components they are all packaged on one single silicon die, and then that silicon die is then packaged into cases like this, or maybe cases like this on the right side, which is more modern approach to MCUs. So the main difference is that everything is inside of one of these little silicon chips. You can also then have other peripherals here, so like ADCs or digital to analog and analog to digital converters, and many other peripherals, or what is needed for controlling some external hardware or some mechanical devices. And that's what microcontrollers are doing. So they are controlling some hardware, and that can be some mechanical devices, electrical devices, everything practically from washing machine to pacemaker to some space hardware. Everything can be controlled by the microcontrollers. So how they control those things? So they monitoring on their pins what is happening. So they monitoring electrical signals on these pins here, and then based on what is on the input, then they can set some other pins to some other states, and that will then trigger some actions in some hardware. Depending of the field in which they are used, there are different standards which have to be applied for the software which is written for these mini computers. And some of these standards, especially let's say in the medical industry, can even force you to do some more serious testing of your software, and will also ask you to have a decent amount of tests, and it will also ask you how much of your real code which is written into these microcontrollers is covered by your tests. Let me show you one simple example. Let's say that in the software for your microcontroller you have one very simple function like this. So the function takes as input an integer and it returns its absolute value. So basically, if it's negative, it will return positive number, and if it's positive number, it will return the same number. One simple test case for this function can be a function like this one, in which you just check what happens if you put inside -42, whether you will get 42 back. Of course, in practice, you will probably use some library functions, or you will use even some frameworks for testing, but it's just for the demonstration, or for this talk and the demonstration of the basic idea. When tests are more complicated, then you'll see that it will be rather hard to understand whether one test is enough or how many tests you need to write in order to cover majority or even whole code inside of this function. If you analyze this test yourself, or maybe ask your colleagues, you might figure out that this test covers only these first two lines, because you just put negative number, and when the number is negative, negative number will be returned. Of course, this is very trivial thing, but if you have a lot of these tests, it will be rather hard for you to do such analysis, and you will never know how much of your real code is covered by your tests. And that's what's the main point of code coverage tools. And now we are going to see how to use one code coverage tool, which is called Squish Coco. We'll see how to set up such a tool and how to use it on the microcontrollers. So the first thing is that after the installation of Coco, we have to tell Coco where is the tool chain which is provided by the manufacturers of the microcontrollers, where it is installed on your operating system. In this particular case, we'll use a microcontroller for Atmel, which is currently a microchip, and we'll use GNU tool chain. So we just have to tell our tool Coco where is your tool chain for your microcontroller. And then you have to do the same thing but the other way around. What you see here is the integrated development environment, or IDE, for the microcontroller, which I selected for this demo. Inside of this, in the setup for this tool, you have to say that you want to use Squish Coco as your tool chain when to instrument the tests, and that you get good coverage of your results. That's in general, this process in general is true for any kind of compilers, but just in the case of MCUs, because they are rather small and limited devices, there is a limitation of how to get data back from your tests. So tests are executed on the microcontroller, and then you have to find some kind of way how to get data back. So how do you know that some functions are actually executed? For that special case, Coco has 3 additional custom I/O functions which have to be implemented inside of the tests, and their implementation will depend on what you have on your side. Let me show you how the functions are implemented by default when you don't have to implement them. So in case if you have a file system, so this is what these 3 functions are doing. So basically they are opening files and adding some bytes to the files. But usually on microcontrollers you don't have this luxury because they are very, very limited environments, so there's no file system, there's nothing remotely like that. It's just the program which you compiled and created using the SDKs provided by manufacturers of MCUs. Once when you put them inside of your MCU, and once when they are executed, there's simply not enough space for file system or anything like that. And then there is the question like how will you get back data from MCU? How will you get code coverage data back from MCU? And then there are several ways how to do that. If it happens that your MCU is used in the application which has TCP/IP or some network connection, then you can just implement those 3 functions so that they use TCP/IP and send data back via TCP/IP. The same idea is that if you have some serial or comport-based communication with your MCU, then you can use that way, that channel, to communicate with your tester's PC and to get data back. The same thing is for CAN bus, and also if some ARM cores have this special module called semi-hosting, which can help you that you can write files on host, that you can write files inside of the targets, and then they will be automatically transported to your host. But it could be that you might not have anything of this here, and then there is still the last option which I'm going to demo in a few moments, is that you just store all code coverage data in one local variable, and then you use debugger to get the value of that variable, and then you forward that to Squish Coco, and then you can see what kind of code is covered or it's not covered during the execution of your test scripts. So I'm going now to show this to you in one little demo. Before I show to you how the IDEs look like, let me just introduce you a little board on which we will be using to do this demo. What you see here is the development board for this SMD21 microcontroller, which is these days rather popular microcontroller. And as you can see on this board, there is no memory, there is no flash, there are practically no additional hardware here. So this thing here is microcontroller, this is just a button, and these things here are just some voltage level converters. There's even no some additional electronical parts like crystal oscillators, because everything is put inside of this chip. So in order to connect this chip with computer, you need some additional external hardware, and in this case we use Atmel eyes, and that help us to connect our development PC to this board. and that's the way how you actually write stuff, how you write your program inside of this MCU. So there are a few wires which are connected to this little electronical device, and then that electrical device is then connected to the PC. The USB connection which you see here is just for the power. Okay, now it's time for the live demo. What you see here is the Microchip Studio or Atmel Studio, and that's the integrated development environment which you use to write software for microcontrollers from Microchip or from Atmel. This is a very simple project. It contains only one C file. In that C file we'll have these two functions which I showed to you in the slides. I've already set up this in order to save some time. I've already set up the tool chain and all what is needed for this demo. So in the terminology of this environment, they call this tool chain flavor. So it's just specialized, a little bit specialized version of tool chain for this compiler. So what do we have here? So this is our function which we want to test. This is the simple test case here. What you see here are these three functions which I mentioned before, which will have to implement, and this thing here is the main function. So when the microcontroller is restarted, this is our entry point. Inside of this entry point we'll set up the port so that we can toggle one LED just to see if the tests are passed. Then if everything is okay, we'll just turn one LED on. And when all of that is finished, then we'll call this special function which you can see here, which will then invoke or use the special custom IO functions, which I will just going to show you, and will save or store the code coverage data inside of this local variable. What you see here are some if-defs which can just guard or isolate this code so that you can build the same code without any kind of instrumentation or influence of Coco. So if this variable is not defined, then all of this practically does not exist. These three functions are implemented in rather simple C way, so just some characters are added at the end of this stream. We have a dedicated blog article about this, and you can get this code, so it's not a problem to share it at all. The main point of all of this is that code coverage, so the execution, once when we execute our tests, then all results will be here in this code coverage variable. So once before I execute this, let me also show you what are specifics once when you compile this project with the Coco tool flavor. Okay, I can build or rebuild that. You will get one additional file which has extension CSMES. So that's the file which you can open with the special Coco tool called coverage browser. So this CSCMS is the actually database of the old code which is instrumented. Currently nothing is executed, that's why you see these lines are just grayed out. But once when we execute this code on microcontroller and get the execution report back, so when we get information about what is happening during the test execution, then you will see that some of these lines will be green. Okay, let's execute now this test case. I'll just go with the simple line by line stepping so that you can just see what is happening. So now we are in the main function, and we'll just execute one by one line. So this line just sets the output port to be this one special LED port to be output port. Now we will execute the tests and check whether the results of the tests are okay, positive. Okay, in this case they were positive. And now when I execute this line, then you will see that one LED will glow on our little demo device. And after this I will save the coverage data. Now since after the coverage data is saved, all data is here in this variable, and then you can even expand and see the content of that variable. Of course this is a little bit hard to read manually, and the good part with this environment is that the environment itself has embedded built-in GDB server and GDB console. So this is the standard GDB which you can use. So the standard commands from GDB work here just fine. So we can, let's say, print the coverage variable and see what is the value of that variable. What we can also do, we can actually then dump the value of this variable into file. I'll just put it here. I'll just type it here. So that's the file which will be in parallel to this CSCMS file, so that the coverage browser can pick it up automatically. The location itself, of course, that doesn't matter. It's just that it is a bit easier if we put it there directly. So let me just type this. Just a second. And the sorry, I forgot to edit what I want to dump. So this command, of course, needs the name of the variable which we want to dump, and that will be, of course, coverage. The dumping of the value into the file failed because I made just a simple typing mistake. So this is the correct file, and now since I executed this, this additional file got generated, and that means that inside of this file we have the whole execution report of what just happened. Let's load now that execution report inside of Squish. We can just name it here. Okay, it was the negative. It's just the name of the import, and then you will see what happened during the execution of this test case. Since the number was negative, then we enter into this part of the branch, and this line 9 is not executed at all. Let me just show you to do the opposite thing. So let's just say, for example, that we want to test what is happening if this is a positive number, so that the other part of the code gets executed. So we'll actually do the same thing again. Now we'll go here maybe a little bit quicker, and we can go back again to the GDB console, and again then actually just use the same variable and dump the same variable. The advantage of dumping the value of this variable into these specific files is that, as you can see, the code coverage already notices and monitors what is happening on the file system, and then you will get automatically asked whether you want to import this new code coverage result, which we are going to do. And now, as you can see, the situation is opposite. So this line number 9 is executed, but this line number 7 is not. As you saw, it was a little bit challenging to type all correct parts here in this GDB console, and then you might also ask yourself, how could I automate this? Can we maybe add this somehow inside of the CI systems, so when there are no humans to click or type anything here, can we do all of this from command line and have some scripts which automate all this process? And the answer is, of course, yes. So this is what we are going to do. I will close the IDE and show you how can you do the similar stuff from the command line using command line tools. I'll open now this OpenOCD command line prompt. OpenOCD is open source GNU GDB server. It happens that support very nicely MCU, which I'm using in this demo, but for some other microcontrollers you might want to use some other GDB server. I will open now the command line tools for the for this particular microcontroller, which came from the microchip or Atmel, so the manufacturers of the MCU. And now I will navigate first to my project file. And then I'll just start the GNU GDB client here. This is the name of the GDB client for this particular toolkit, and I'll specify the name of the file which I would like to load inside of the inside of the microcontroller for the execution. And now we have the same situation, so this is the same GDB console like what we saw in the IDE. If you just print the coverage variable, you will see some data here, and then we can also use the same dump value function to dump the value. I'll just say here, since we are already inside of the project, I don't have to specify the full path. You just have to get the right name. And as you can see, that's already written down, and the Coco, which is running in the background, notice that we just have to give it a different name, and then we will load this execution in the Coco browser, and you can see that the same code, because it was the same test, so the same thing is executed and we got the same results. So that would be, in short, how to use Coco with the code coverage on the MCUs. And let's now talk a little bit about the common challenges and the problems, because as you saw, the MCUs are rather a limited environment. They have in general way less memory for program and for the instructions. The sizes are usually in kilobytes, although these days we start seeing the MCUs which have 1 megabyte or more of both RAM and flash. Because we are working in the limited environment, we have then to configure Coco to use or to generate instrumented code which has a little bit smaller size. First, we don't want to instrument everything, especially things which are not needed, like startup files or similar things. And then we can also instruct Coco to just generate simpler API. For example, we might be interested in whether one function is called, not how many times it is called. So it's just interesting. It could be just interesting for us that the function is called only once. And then the general idea of what you saw with GDB server could be that you compile one part of your code and you execute only one test. You get code coverage back on your PC, and then you compile a different test and execute that test. Squish Coco supports merging of the different code coverage reports, so that at the end you can get the report for all of your code, but just it's not executed in one go, but like in some kind of batches. And this is also what is very important for automation and CI. Different tools have different options how to execute things from command line, but in general everything should be possible to execute from command line, from building of your project to downloading into your project. So like using this AT programmer command line tool, you can program your microcontroller from command line as well. And as we saw, you can do debugging from the using GDB server, either from OpenOCD or from some other manufacturers. That would be all for this talk. I hope you learned something new. Thank you very much for your attention.